All right, so we're going to go ahead and get started in chapter 20. The big thing is we'll remember that in statistics, we don't put our faith in what the statistics do say, but sometimes what they don't tell us, what they're not including. And we're going to talk about that and how that applies here. We're going to talk about hypothesis testing about a single proportion. What this is, the goal of these tests is to determine the evidence provided by some data, by a sample or an experiment in favor of a claim about the population. Now, what that means is my p-hat, is my sample proportion, is it real? Does it represent what the population has, or is this just random chance? Is it just sampling error? Now, our lesson is going to focus on the single proportion z-test, or the one sample proportion z-test. Now, a couple terms we have to have. The first one we're going to have is called the null hypothesis. Null just means nothing. There's nothing there. So the null hypothesis, there's nothing happening. That just means that it's a statement that there's no change or no effect in the population. There's nothing to measure. Now, alternative hypothesis, this is a claim about the population we're actually trying to find evidence for. We can't prove the null hypothesis, but assuming it's true, we can look at how likely was our experiment to have happened. Both of these are written in terms of the population, not in terms of our sample. Our sample is what our sample is. However, we will have written these before we've gotten our sample, or we're supposed to. P-value. This is kind of a complicated idea. All it is, though, is the chance, the probability, that the observed statistic took on a value as extreme or more if the null hypothesis was right. The closer this probability is to zero, the stronger the evidence for the alternative hypothesis. This is also called the observed significance level. And what we mean is that if our null hypothesis says the proportion is supposed to be 50-50 or p is 0.5, then the likelihood of me getting a result of, say, 10% should be fairly low, depending on my sample size. And if that's such a low probability event, it was so rare, well, that's kind of suggests maybe the null really isn't 0.5. So p-values, you actually want low p-values. P-value is, again, it is not what your sample proportion is. It's the probability you'd have gotten that proportion if the null were correct. Now, statistical significance, let me move this just in case it's going to be covering something we need to see. Statistical significant, what this means is what it means is that the result statistically has merit. However, it doesn't mean the results are necessarily important in a practical sense. It just means it was unlikely to have been chance for our result. Now we're going to use z-scores for these. This is our test statistic is a z-score. That's why it's called the one proportion z-test or the one sample proportion z-test. And we're going to end up covering something we need. All it is, it's our z-score for our sample proportion or our p-hat minus the null hypothesis p-value divided by the standard error of the null hypothesis's p-value. Remember, at this point, we're testing our statistic. We have not discounted the null hypothesis, so we're going to treat it as though it's true up to this point still. Then we have two types of tests we can use. We have the one-sided test or the one-tailed test. This is a test that's only interested in deviations from the null in one direction. In the picture I have here of a critical region shaded in red, that would be less than the null hypothesis. So if I was only looking for less than, I'd shade away from the mean, moving downward. I could also do a one-sided test for greater than, and my critical region would be the other side of the p-hat. Two-sided test is just that. This is a test that's interested in deviations in both directions. This may be an alternative hypothesis that, let's say historically 40% of students have gone to their ring dance. A null hypothesis is interested in both directions. Alternative hypothesis in both is if I was to say, well, I think it's different this year. I'm not claiming it's more. I'm not claiming it's less. I'm just claiming it's not 40% anymore. In which case, I need to look at a critical region on both sides of the mean because it could have changed in either direction. And we'll go over how we mark these in a moment. This is just the terms that we're going to use. Now, significance tests, again, they ask us how unlikely was my observed outcome if the null were actually true. Our goal is to gather evidence in favor of the alternative hypothesis in order that we could reject the null. Remember, we can't prove the null. We're not trying to prove the null. We're not trying to prove it's false, or to a certain extent we kind of are. We're looking for our results and say, well, how likely or unlikely were they if the null were true? And we have a little saying to remember this. It said if the p is low, so probability of my sample taking on this value, if this is low, then the null got to go. I'm going to throw it away. I'll reject the null hypothesis. So if you remember, if the p is low, the null got to go. Now, there are some steps for how we're going to run this. We're going to run our hypothesis first. We're going to come up with it. We're going to identify the population of interest, identify the parameter we want to draw conclusions about. And then I have to state the null and the alternative in both words and symbols. Now choose and state the model I'm going to use to make my inference. I have to state the assumptions, verify the conditions to validate those assumptions for that procedure. Now, as of right now, we're only going to have the one model, the one proportion z-test, but we will have more we're going to add later. Now, for the one proportion z-test, our assumption, first one, is independence. This isn't new. We use it in chapter 19. We've used it in chapter 18. To have that, I have my two conditions. I need randomization. I need to meet my 10% condition. Do not sample more than 10% of the population. If you do, you're going to violate the independence. Next thing I need to know, was my sample big enough? If my sample's big enough, then I get to use a normal distribution. In order to have that, I need my success failure. N times P and N times Q have to both be at least 10. Now, I want to emphasize this. I have to emphasize this point. This is N times P. This is based on my null hypothesis. This is not N times P hat. I'm not worried about my sample yet. All of this should be done before you actually do the survey. If my null hypothesis says I expect approximately a 50-50 split, then my N times P is going to be my sample size times 0.5. Whatever I actually get with that sample, that's P hat. I'm not using that yet. At this point, I'm still using my values for my null hypothesis. Once I've met that, if I meet my conditions, then I can do the mechanics. Then I can carry out the actual inference procedure, which is going to be calculate the test statistic, find that z-score, and then find the p-value for that z-score. What was the probability of getting that result based on our hypothesis? Then state my conclusion. I want to interpret my results in context of the problem as a statement about the alternative hypothesis. My ending of my statement should have to do whether or not I had evidence for the alternative. I'm also going to talk about the null, in that I either rejected it or I failed to reject it. The way you're going to decide this is you're going to ask yourself a couple questions. First, were you surprised? That's going to answer the question about whether or not you should reject the null hypothesis. But to decide if you're surprised and how surprised you are, you have to look at the p-value. The lower the p-value, the more surprised you are. It would be a rare result. That would mean, yeah, we should be kind of surprised by this. Lastly, what would not surprise you? You want to create a confidence interval in order to say, well, these results, you may be 95% confident the true proportions between A to B. Knowing that, those kind of results would not surprise you. A confidence interval should almost always accompany the hypothesis test. So you should be doing these almost every time. So let's try an example. So in 2010, U.S. Consumer Product Safety claimed 90% of all homes have at least one smoke detector. City Fire Department, they ran a public safety campaign about smoke detectors. They put posters, billboards, ads on radio, TV, and the newspaper. The city wanted to know, was this worth it? Did we get above the 90% national rate? So they grabbed some building inspectors, sent them out to 400 randomly selected homes, and found that 376 of them have smoke detectors. Our question is this strong evidence the local rate is higher than the national? The way I'm going to answer this question is I have to go in and check my sum conditions. I'm going to figure out the whole steps. Null hypothesis, alternative, work my way through everything. Step one, my hypothesis. Null hypothesis, there's no effect. Nothing happened. We are no different than anywhere else. The alternative, what we want to try and prove, was it had a positive rate, so our compliance would be higher. So this is it in words. Null hypothesis, our city is no different than anywhere else. Alternatively, the public safety campaign worked, rate of compliance is higher. I have to define my parameter of interest. P, the proportion of all homes that have smoke detectors in the city. So my null hypothesis is that P is 0.9, that we're no different than the national average. My alternative, what I want to prove, is that P is greater than 0.9. And again, make sure we're using P, not P hat. The other thing we point out is that in our null hypothesis, we've used equals. Our null hypothesis is going to use equals. Our alternative might use equals. I'm sorry. It may use greater than, it may use less than, or it could use not equal to. It depends on the way the question is phrased. In this case, we want to see if it was higher, so we use greater than. Now, first thing was, it said we had a random sample of 400 homes. So we've met our randomization. We assume 400 times 10, that'll be 4,000. As long as that's less than all homes in the city, we're going to meet our second condition, so we've met our assumption of independence. Our sample is, and one is relatively independent to another. We look at our successes and failures, n times p. 400 my sample size times 0.9. That's my null hypothesis p-value. So I expect, on average, 360 successes. I expected 40 failures. Both of those are at least 10, so my sample is big enough to use the normal model. So I'm going to use the one-sided, one proportion z-test. One-sided because I only care about greater than. So I set up my problem. Now I can do my mechanics. So to do my mechanics, there's some things I have to know. One, I have to know my sample size. We said it was 400. Two, I need to know how many met the condition. Well, 376 of the homes out of those 400 had smoke detectors. So I calculate my p-hat, 376 divided by 400, which gives me a p-hat of 0.94. Now I have to find my test statistic. My test statistic is my p-hat minus the null hypothesis divided by standard error of the null. And of course, draw, label, and shade. 0.9, the mean is the mean is the mean. This comes from the null hypothesis because we're saying how rare was our result if the null were true. And if the null were true, we'd be using that for a mean of our sampling distribution. 0.94 is what my sample had. And I used a critical area was greater than, so I shade above 0.94. But in order to do that, I use my z-score, 0.94 minus 0.9, divided by standard error of the null hypothesis. So you notice that's 0.9 times 0.1, not 0.94 in the denominator. It gives me a z-score of 2.67, which goes right under that 0.94. And now I want to look up what is the probability of getting a z-score of 2.67 or more, which is going to be equal to probability of my p-hat taking on that value, which is a probability of z would be greater than 2.67, and that's 0.004. And I found that using normal CDF, as we've been using up to this point. So my p-value, again, is 0.004. That means I had a less than 1% probability of this result. That's very low. It's unlikely this observation is just due to sampling error. So I reject the null hypothesis. In fact, this is strong evidence the city has more than 90% of homes have a smoke detector. That low p-value suggests the null was wrong, and that's evidence in support of our alternative. That's how hypothesis testing works. So lastly, I want to interpret it carefully. If it turns out the city is actually 90%, the same as everywhere else, there is a 0.4% chance of this sample happening. It would happen about 1 out of every 250 times. So you can find that by doing 4 divided by 1,000, and simplifying, you'd say it's 1 out of 250. So we do expect this to happen sometimes just by chance, but it's just really rare, and that's why it's evidence for the alternative. But about that many would have 94% or even higher. Now, that could be happening, but it's not the most logical. In fact, constructing a 95% confidence interval for my sample, I'm 95% confident that between 91.7 and 96.3% of the city's homes have smoke detectors. Now, There's still a 5% chance it's not within those areas. Maybe it's a little less, maybe it's a little more, but I'm 95% confident it's between 91 to 96 or 92 to 96%. So let's try this again. And at this point, go back, review the previous question, look at the steps, and we come back to this question, have you try steps. Pause the video as you try to work through some of these questions. So we have 20% of a bag of M&Ms is supposed to be orange. Suppose a bag had 122 candies in it, but only 21 were orange. Does this contradict the company's 20% claim? So first thing is, when you come up with our hypotheses, this one's a little tricky. You may come up with it one way, you may come up with another. Try and pause the video, think about the null hypothesis would be. And then the alternative, what are we trying to prove? Okay, so if you're playing, you must have gotten through it. Well, to find the primary interest, P, the true proportion of orange M&Ms. Our null hypothesis, in symbols, our null hypothesis is that 20% of the bag is orange. There's no effect, no difference. It's living up to what the company says. Alternatively, this is where the wording of our question is a little odd. It says, does it contradict the 20%? So that doesn't just mean less than, it could also mean greater than. So either my null alternative is that P is not 0.2 or just not equal to. So this would be a two-sided test. And we'll go over how a two-sided test works now. So my model, well, I need my independence assumption. It is reasonable to think that M&M colors are independent, that they don't affect each other. If you get one that's orange, that should be independent from what another M&M turns out to be. Random sampling. 122 M&Ms could be considered representative of all M&Ms and to be a random sample of M&Ms. 10%, well, 122 times 10 is only 1,200. That's pretty certain that's less than all the M&Ms on the planet. So it looks like my independence is going to be met. Big enough sample. Again, now I have to go back to using my P, not P hat. And this one, N times P would be 122 times 0.2, or 24.4. N times Q, 122 times 0.8, 97.6. Since both of those are at least 10, the sample is large enough, I get to use the normal model. So I will use it for the one proportion Z test. And since we're testing hypothesis that it's different than 0.2, we're going to use the two-tailed test. And we'll go over how we're going to do that. First, my mechanics. I need my sample size. We said it's 122. Then my X, 21. We said 21 out of the 122 are orange. Using that, we find our P hat is 0.172, well, roughly. It's, round off a little bit. Then I draw my curve. And this is a two-tailed test, so I have on both sides. This would be the proportion of orange M&Ms. This is my sampling, my distribution of samples. First, I put my null hypothesis value, 0.2. Then I had my sample was 0.172, but I need it on both sides. So I take 0.2 minus 0.172, and that gives me the difference. Then I add that back to 0.2, so on the top is going to be 0.228. In my z-score, though, I only use the lower one. So 0.172, my p hat, minus my p, divide my standard error of p, or a z-score of negative 0.77. So my z-score is negative 0.77. That means my upper side, because it's symmetrical, it's going to be positive 0.77. Nice symmetrical curves. So what I'm going to do is, since both those areas are the same, I'm just going to double one of my areas. In this case, I'm doing p hat being less than 0.172. And now I'll find that area and then double the probability to have both combined. That's the same as saying 2 times the probability z would be less than negative 0.177. Using normal CDF, I have a p-value of 0.44. This is not a rare occurrence. I expect a bag to show up like this, maybe to be this far different 44% of the time. My p-value is very high, so I fail to reject the null hypothesis. I do not have evidence to suggest the proportion is any different than the advertised 20%. In fact, if I ran a 95% confidence interval, I could say that the p could be anywhere from 11% to 24% based on my sample. Well, 20% is in that confidence region. 20% is not surprising then. I expect it to happen. So We can also run these tests on the calculator. To do this, we use stat, then we're going to go to tests, and we scroll down to the one prop z-test. Now when we go into the one prop z-test, it asks us for some information. It asks us for our null hypothesis. In this case, we'd load 0.2. It then asks us for x and n. This is based on our sample. Remember, P naught is our null hypothesis. X and n are from our sample. We then tell it which test we want to run, which was the not equal to the null hypothesis. And if we run calculate, it tells me the z-score, my test statistic is a negative 0.77, p 0.44156. That's my p-value. My p-hat we knew, and n we also knew already. But I need that p-value, I need that test statistic of z. So in this section, now, also, that's if I ran calculate. If you run draw, you're going to see the normal curve, but it won't give you the z-score if you run draw. And to get that test statistic, you need the z-score. So go ahead and run this to get your test statistic, or just do it manually and verify using this test. Homework for this chapter, questions 2, 4, 5, 6, 8, 10, 11, 14, 15, 17, 19, 20, and 23. Again, I'm also going to upload another example questions. If you still have questions, make sure you ask in class. We're going to try some things in class to work with this, make sure we get this mastered. Hope you have a good evening. Look forward to seeing you in class. Have a nice day.